Hi. Yeah, it's really great to have everyone here in London. So my name's Edward Johns. I'm the local chair. Fantastic to have to be back to in-person conferences. I'm going to be chairing this first opening keynote, and we're delighted to have Nando de Freitas with us for the opening keynote. So Nando is a lead scientist at DeepMind, and he did his undergraduate studies at the University of Witwatersrand in South Africa. This was followed by a PhD in information engineering at Cambridge University and a postdoc in AI at UC Berkeley. He was then a full professor at the universities of British Columbia and Oxford before joining DeepMind. Nando, thank you for joining us, and over to you.
Thank you very much. It's so good to be giving a talk again. It's been a while, especially if you're an academic, or used to be an academic for so many years, giving lectures and so on. It's so wonderful to be able to do this again. It's great to see old friends around this room. It's also wonderful to see students. They were always the energy that sort of drove me to continue doing research. Thank you for the invitation. And brilliant work for organizing this conference, though we have some technical glitches. Slide clicker, could it be batteries maybe? It will be just a few minutes. If it helps, I have my laptop. I could connect it directly. Thank you. I guess while we wait, I can go over the title slide. So this talks about data-driven robotics. There we go. I can see the slides back. No. There. Okay. I spent like 5 hours at least on this slide, so I'm glad I can show it to you. So data-driven robotics is an area of robotics that I think is very young. It's about 4 years old, really. That's how long we've been doing RL with robots. There's been an explosion of algorithms and technology, open sourcing, and benchmarks to support it. Most of the work I'll present here will be sort of 2 case studies of what is data-driven, and then I will try to go over some points which are kind of, for me, like important lessons that I learned along the way working in this. And of course, even though it started in the last 5 years, and mainly thanks to some amazing work by some of the not just my colleagues at DeepMind, but also some researchers who've influenced my thinking, like Andrej Karpathy and Anka Dragan and a few others here. And it may have started perhaps a while longer, but it's really only over the last 5 years, I think, that it's been taking off. Okay. At the core of data-driven robotics is the idea that all data is precious and all data should be stored. I think most people, when they do an experiment with a robot, they usually dump the data somewhere and then that data gets deleted. I remember approaching someone at teleoperating a robot arm at a conference a few years ago in Barcelona, a robotics conference. I can't remember which one, Iris or ICRA, one of those. And I asked them if they were storing the data, if I could get the data. And they were, why? Why would you want to save the data that you used to teleoperate? The currency of machine learning is data. That is one of the most important things. And if you're not storing your data, then you're kind of stopping. In a way, we're used to releasing our papers, but I feel like if we were releasing our benchmarks and our data, we would make as much progress from that as from reading the papers on archive. Data is really precious, and hopefully in this talk I will sort of show you some examples that argue for that. All data should be stored. In fact, at DeepMind, we call this never-ending storage, and there is actually a software platform that supports this. Everything gets stored. So whether you're collecting demonstrations by teleoperation or interacting with the robot in some way, whether you're collecting data from running robots in simulation, or all sorts of things that people do here, play and so on, random policies, the advice that I would give you is store the data into a proper database, not just dump it in some place. So invest some time on learning about databases and storing your data properly, if you're not doing that already. Think of how to annotate that data, or how others could annotate that data, keep improving that data over the years. And because from the data, we can learn all the sort of important things for control. We can learn cost functions, we can learn reward functions. From the data, we can learn policies. And over the last few years, we've seen a lot of progress in a technique called offline reinforcement learning for learning from data. How many people here are familiar with offline RL? Just to gauge, okay, the majority. Online, I hope you are too, but I will sort of cover the basics of this. And finally, evaluation, which is about running the actual robot. And that is actually quite hard. So the second example here in my talk will be all about evaluation. And of course, this never ends. It's a never-ending circle. You cycle, you keep collecting data, you keep annotating data, and so on. So let's go over the first example. And the first example is from this old paper on offline RL. And here we had a simple platform with a robot arm that manipulates 3 objects, red, green, and blue, of different shapes, and has to do different tasks like stacking and so on. The data for all the tasks was stored. The demonstrations that we collected were stored. Running different agents, every run, whether the agent was working or not, got stored. Random policies were stored. All the data was stored. And we were able to eventually learn from all the data. And in fact, the more data we have, so these experiments we've done is the more data you have, the more you can learn. As an example of how you can collect data, here is teleoperation. Here we were just using a simple space nav to do stacking. Stacking is actually quite hard. It's seemingly simple, but it requires understanding the interaction between these 2 objects. It's much harder than just picking and dropping in a box. That's the sort of thing you would use for fulfillment. And to learn rewards, the team that worked on this project came up with this interface where what they do is the user watches a video, and then she draws a sketch, and she in this case was mostly Xenia, drawing a sketch of how close to the reward you're getting. So if the darker blue line is near the top, that means you're getting a high reward, so you're very close to a perfect stack, and then before, you're sort of further down from attaining the reward. And the idea for doing this is essentially to collect pairwise preferences. And instead of just comparing 2 episodes and saying which episode you prefer, which is just one data point, one label, by drawing a sketch, you can now take 2 points in that curve, as we'll show there on the left-hand side with 3 red dots, and you can say the red dot that's higher up is better than the other one. And so you can now, essentially, you're collecting preferences of what is an image situation that would bring you closer to the reward, and you're collecting n-squared of these. So very quickly, you collect a ton of supervision data. this question of designing interfaces to quickly understand what the human wants, what is the reward function, I think is one of the most important ones in robotics right now. Anka Dragan at Berkeley has been doing amazing work in this area, and I think a lot more is needed. It's like a robot comes into a scene, should very quickly learn what are the preferences of the users and how to satisfy those preferences. The other thing we did in this project that often we do is offline RL, because once we have a reward function and we have a lot of demonstrations, a lot of data produced by agents and humans teleoperating the robot, we can use this technique called offline RL. I'm just having trouble here with the clicker. So first we learned these sort of reward functions, and then once you have a reward function, you can apply a reward model, you can apply it to all your data. The whole database can be annotated with the data. And then the next thing we can do, as I mentioned earlier, is offline RL, where we take the data annotated with reward functions, and we can use it to learn policies. And importantly, in offline RL, we don't need to run things on the robot. So it's cheap from that perspective. So everyone could basically take a data set and learn a policy without having to deal with the hardware. Now, why not do just imitation? So here's sort of a brief introduction to why we would do offline RL. So in imitation, in traditional, what we do is supervised learning. So if we have data of trajectories, we could try to map the observations to actions. And so the problem with supervised learning is it's only as good as the data. If the data was produced by an expert, that technique actually will work quite well. If the data is, however, produced by random policies, then you're going to end up with an average, and so the quality wouldn't be that high. And so a good way to think about supervised learning or behavior cloning, as most of you know it, is that it's like having a teacher that shows you how to do things, but then you're on your own. The teacher doesn't bother to come and look at your results and grade them. So you never get that extra feedback. With offline RL, we add rewards into the mix, and through the rewards, we're able to actually say which parts of what you're doing well, and which parts you're not doing well. So it has an aspect of selective imitation, where you're not only mimicking what the expert does, but you're learning which bits of what the expert does are worth imitating, and which bits are not worth imitating. And in fact, if you have several experts, which bits of what expert will you learn to imitate? This aspect of selective imitation, I think, is very important for dealing with very large databases. And in fact, is one of the ways in which many of us learn. So here's a simple picture that illustrates the idea. Suppose you start at a state in a simple maze, here indicated by a blue diamond, and your goal is to get to some treasure here, some reward state indicated by this yellow cell. From the first state, you take an action and estimate the parameters by backpropagation, and that would give you a policy that would just follow the gray line. So it would not be very useful because it wouldn't get you to the reward because it's suboptimal. It never touches the reward. So it doesn't make sense in non-expert data. Now, it would be great if we had an oracle that told us these are the good bits of what you did, and these are the bits that I wouldn't advise you to do. Because if we had that oracle, then we would just imitate what's good, and where it's red, that is not good, we would then try to do some sort of RL exploration. And that is the idea of many offline RL algorithms. So I'm instantiating one here, critic regularisms for choosing from what data to learn. So you can have lots of data. Some can be non-expert data, but if you use the right algorithms, you can still take advantage of all the data. In short, even if you had a bunch of random policies, and one of those random policies happened to hit the target, and you just store those random policies, then you can learn an offline RL agent on that random data, and it will learn to do things well, and it will probably be superhuman at how quickly it can do, say, one of these things like stacking. And finally, evaluation. One of the hardest things in robotics. You get to eventually try it on the real robot, and you again will get some performance, and you should store that performance. And there's been a lot of work recently as to how to do this, how to optimize this process, because evaluation, as you know, is very expensive. Running the robot is expensive, and so you want to try to minimize the number of evaluations. How to choose the hyperparameters and so on of these policies when you have to rely on evaluation that actually involves running hardware is also difficult. And again, in that area, there's been some interesting research recently. So by doing offline RL and using these reward sketches to learn the reward functions, you can sort of learn policies that do this sort of thing. They learn to stack. They're fairly robust to changing the shape or someone trying to sabotage what the robot is doing, and some unexpected initial situations as well. And here on the right, to just get it right all the time. So if you think about the applications of robotics out there, the only place where we can sort of deliver satisfactory robots and industries where they have that consistency. If you have a self-driving car, you want it to always do the right thing. If you have robots in a factory and so on, you want them to do the right thing. They can't just get it wrong now and then. We have that sort of tolerance in a lot of areas of machine learning, but in robotics, because this ultimately involves machines acting in a physical world, we have to strive for consistency. So with this in mind, some of my colleagues at DeepMind decided to sort of take this work forward and actually create a benchmark with a lot of object diversity, and where they control the object diversity. I think this is research that's being spearheaded by the robotics group at DeepMind, and Francesco Nori and Ryan Hatzel are here. And this work is being presented here, I think. Okay, so you'll see it at one of those beautiful hybrid posters, I think. And it's a platform that allows them to come up with automatic evaluation and very clear metric, which is easy to define, of stacking one object on top of the other one, red on blue in this case. I have an ad here that says that the TV will turn it off in 5 minutes. Hopefully that will not be the case. Okay, let's hurry up then. So they consider stacking situations. In the poster they'll give you more details, but stacking can be very hard because your objects can have shapes that make it very hard to grab, or make it very hard for them to stand still on top of a block, or require some geometric reasoning about and turning around, to make sure that you can stack them. So this problem can be made as easy or as complex as you want. They consider these 5 situations, and then they create a huge training data set which has the sort of 5 situations. That's one task. You master each of these 5 skills. And they also create a data set that's about generalization, where at some point you will encounter objects that you hadn't dealt with before, and you want to see how well you can do at that task. They tried many things. This is what worked for them after months of trying. First thing is to start with simulation. And in simulation, you essentially come up with one of the best RL algorithms you can come up with, and you learn a policy. And because you work in simulation, you have access to a state. So you know the exact location, for example, of the block. And so you can learn from state to map from state to actions for each of these 5 tasks. Once you have that, you can use neural network distillation of the policy to learn to, and I'm going to say a bit more about this soon, to learn to convert a policy that goes from states to actions to a policy that goes from observations to actions. And they do domain randomization as part of this to get some robustness. And finally, they deploy that policy in the robot. And from deploying that policy, they collect data, and then they can do offline RL on that data to get a policy that's even better. So often doing well at this involves doing a lot of things. And so here's the performance. So they're comparing a human doing this task, teleoperating, versus a scripted policy. And the SIM2Real, just by distillation, already works much better than if you were to, say, use a scripted agent, so if you were to write the code. And when you do offline RL on top of that, you get up to 82% performance. So this is great for stacking, because stacking from pixels and with a real robot, because 5 years ago we couldn't do this. I still remember about 4 years ago when we finally got this robot to put one block on top of the other one, and it only worked 10% of the time, and it was amazing. But the stacks actually turns out to be incredibly hard. These numbers also tell us that we're very far off from doing this well. And so a lot more research is needed in neural network architectures and so on to get this right. But now the nice thing is we have a well-defined metric and a good evaluation, so we can treat this, which is at this stage still an academic problem, to innovate better methods. And when we go to generalization, we see that the performance is better than human, but it's considerably worse. So the problem of generalization of policies is a huge problem, as you can see here. The TV will be turned off in 1 minute. Press any buttons except the power button. For the tech support at the back, I'm getting a message that the TV might be turned off. So hopefully they'll be able to anticipate it. Anyway, so if you want to learn more of, getting the details, attend the poster. But here are some important highlights of that work. One, because they automated the evaluation, because they used detectors to detect what's a stack and so on. Since everything has been automated, they were able to run this completely offline. So it's great, especially during lockdowns and so on, that the machines could be in the lab actually running all the experiments. The other lessons from this work are that using bigger neural networks works better for generalization. 4 years ago, most neural networks for control were 2-layer convnets. Nowadays, we're using God knows how many stacks, ResNets, and so on. So the network size has increased. There was even this error, I think, in thinking that for control, we only need small networks, but we don't. If you're doing visual motor control, where you're learning perception, you do need massive networks. Interacting with scenes for control is one of the hardest problems. And in fact, if you even look at biologically, the reason why we have big brains is to be able to do visual motor control. Oh, another thing that worked really well here was distillation. And sort of following this list here, I decided to create my own list of what are the things that have worked well for us over the last few years, or the lessons that I've learned. And so let's move to the first one. The first one is the one that I've been trying to hammer here all the time. It is data is really important. Learn to index it. Create visualization, APIs and so on for your data. Data is really the precious thing. And you should store all sorts of types of data. Simulation is a way to get a lot more data, and it's easy because you can run RL algorithms in Mujoko and so on, and you can store that data. You can do domain randomization. And lastly, one thing that I hadn't mentioned about data is also code. Your ROS code and so on, that's data as well. You've seen projects like mapping descriptions to code and so on with transformers. And it would be amazing if we could do the same thing for robotics, if we could just write automatically code for robots to work. But we can't do it because there's not enough data released. And there's a few languages, but actually that's not the problem, because we could sort of overcome that. Mostly there isn't a culture of making data sets available in robotics. And if anything, the big message of my talk is we need to change that culture. We need to start making data sets available, because the data sets are worth a lot. Even if every robot platform is different, the data sets are still valuable. How am I doing with time? Sorry, there's been a few. Okay. So, lesson number 2 is distillation. Again, how many of you are familiar with distillation? Half of you. The other half, I highly recommend that you Google it and start learning about it. Because if you're doing behavior cloning, you should really consider doing distillation. So distillation is already showed is very useful when you can learn a policy in simulation and you can have access to states, because learning from states is a lot easier than learning from sound and pixels. And then distillation is about a student learning to copy a teacher. So typically, as the first point in this slide, if you have n teachers, capital N teachers, indexed by small n, and the idea of distillation is essentially you create a KL divergence where you want to fit all these teachers, and you're learning a student here with a small p. If you do this well, and there's several papers out there with the math, Google any paper by Nicholas Heath and we'll have some derivation that will give you this equation. The student ends up being a mixture of the experts. And the mixture proportions is this term probability of expert n given a state. So that term tells you, given a particular state, what expert will be responsible for that. Now, to get a better understanding of this term, of this equation, think if there is a state that only one expert visited, then that expert will become responsible for that state. So P of n, given that S for one expert will be 1, it will be 0 for all the others. So at that state, you will only imitate the expert. If you have a good expert for that state, that's great. But if you have a random, if someone visited that state by random, then you're copying a random policy on that state. So that's not going to be great. If you visit a state, if 2 policies are responsible for a state, what you end up doing is you average. And that also may not be a good thing, because the average decision might not be the thing that you want. But that's effectively what happens when we try to clone n experts. But one thing we can do, and that's an old idea, goes back to Dagger, the idea of Dagger for imitation, is you can, suppose you have only one expert, so you have many experts produce the data, including, say, random policies. But now you evaluate one single agent, and this is typically where it would make sense is you've been training an agent in a, say, Mujoko, and it's only after, say, many iterations that you have one that you like. And so you want to save that one as the expert. But of course, to get there, you tried many policies that were suboptimal. But you don't want to discard the data that those suboptimal policies produced. So what you do is you keep the data, keep all the states, and then you evaluate the expert at all this other data. So you get evaluations of the expert. So you have now an expert that applies to not just the data that was produced by the expert, but to other data. So you have a wider coverage of where that expert is. Having a wider coverage, you now learn a student that imitates the expert. So where this helps is, if you had data only for the expert, for example, for driving, the expert will just say drive in the middle of the lane. But the moment the expert sort of veers a bit off the lane, it encounters a state that it's never seen before. And those and so it might make a small error, veer a bit to the right. And so the errors quickly accumulate exponentially, and the expert goes off the road. But if you have more data that tells you what's going to happen when you veer a bit off, then you have the hope to have learned what to do there and get back on track in the middle lane. And so this trick actually works quite well. Of course, if you eventually have states that are very remote, like, I don't know, a beach, maybe you've never collected data driving there for the expert, and so you likely will not do well. So, but for perturbation of the data, this is actually quite effective. You can get, say, sometimes a 10% improvement in your experiment just by doing this in your policy. And finally, there is this form of teaching the student where, as done in this work that I just described now, where the teacher is fixed, you learn it in simulation, and it goes from state to actions. And then you use a student that learns. So you fix a teacher, you put it in that loop there on the top right, and then you insert a student. The student generates an action. It's the action of the student that changes the environment, but the teacher will produce an action for that state of the environment. And then the student learns to imitate the teacher over time. But while the student is learning to imitate the teacher, only the student learns, not the teacher. There's no gradients going through the teacher. And it's the student that controls the environment. This is an example of what Pedro Ortega calls counterfactual teaching, and there's a recent paper by him on this. And this ensures that the knowledge that the student gets here is actually causal knowledge. And it will avoid some traps, which I will point out at the end of this talk. So this is a great way of learning through interactive distillation. Another very obvious lesson, I've already alluded to it, is big nets are important. This is a result that everyone knows by now. The bigger the nets, the better generalization you can get. There's only one caveat here, and it's that if the nets can retrieve data in the world, they can actually afford to be smaller. RL agents were typically small because RL agents are always gathering data from the environment. So if you can reactively gather data from the environment to help you with your decision, you don't need such a big brain. However, I think these are two sort of frontiers that we need to push. We need to make agents that are better at using the environments to act, and that had retrieval mechanisms. And we've seen a lot of cool work in this area in language modeling over the last few months. But we also need to ensure that our nets are capable to generalize. Just like we've seen for also big language models, we also want to be able to do few-shot. And there's been a few works with robotics and few-shot generalization, where you have a setup where you just give, say, 5 demonstrations, and you want the robot to be able to imitate you. So this continues being, I think, one of the most important problems to deploy robotics out there, because when I get my robot and I want to teach my robot just, I don't know, my little dog robot, like sit, and then I sort of tip it to teach it how to sit. I don't want to have to repeat this like 5 million times. Which is what you would do with RL, but you can't afford to do that in the world. You can afford maybe 5 times or so to get it right. And part of the problem here will be, how do you design APIs for quickly telling the robot what you want the robot to do? You know, how do you communicate with the robot? And how do you allow for interaction? Maybe you teach the robot how to do something, use a mix of language and touching the robot and teleoperation perhaps, and then you have the robot communicate back to you, okay, is it like this? And then you say, no, not like this. I would like you to sort of go more around it to make sure that you don't break the glass and so on. We're very far from being able to engage in these type of dialogues with robots. And I think the problem is because designing such APIs is actually a very hard problem, and we haven't yet invested enough time in this, but eventually this actually is what we need in order to be able to have interacting robots. So we need to think of the interface of how will the human be teaching this machine to achieve different goals, whether it's someone in a factory trying to teach its machine to, you know, maybe like we're going to sand this piece of wood in a different way now, and we're going to do it like this. Now, I mentioned that we should be storing all data no matter what the shape of the robot is. And the reason is because by now we know how to learn neural network policies for robots of different shape. One of the big important things about few-shot learning and meta learning and so on with neural networks is that we can actually learn a core neural network, and we can change an input, maybe go to a place where there is one less camera, or go to an arm where there's less degrees of freedom, and we can still hope to rapidly fine-tune that neural network to do well in that area. And in fact, in some cases, it's possible to parameterize the output so that it becomes independent of, say, the number of actions. So one way to do that is, for example, if you train with many different architectures, and where your actions are just a list, one after the other. So you basically convert your action stream to something like a language model would use. And so in that case, if you convert it to that representation, if you sort of model it as a string, it doesn't matter how many actions you have. You should become invariant. You should learn a neural network structure that is invariant to how many actions you might have to use. Now, hardware keeps evolving. And even when we just basically change a gripper in the lab, we often have to gather more data and retrain, but we shouldn't be always starting from scratch. We should be designing our algorithms so that when you change the robot, when you change a part, when you change the gripper, it still works, or you can fine-tune it very rapidly to work. And it's the only way the data-driven approach will work for robotics, because the field is still evolving very rapidly in terms of hardware. We haven't arrived at hardware that is robust enough. And every lab has a different robot set up. So for us to be able to share knowledge, we can share it at this level, but to be able to share data in a useful way, we also need to start thinking a lot hard about how do you come up with neural network architectures that are invariant. Not just the simple changes of illumination and so on, but actually changes in the actual robot architecture. And of course, another area where we need to continue sort of working on that is very important is perception. And the perception here is slightly different than just assigning labels to an image. Because, say, if you have a cleaning robot and goes into that messy scene, it has to reason about how it will interact with that scene. And that is a far harder problem than just assigning labels to an image, to do image classification. This is, by and large, still one of the, I think, big open problems in data-driven robotics. One work that I really love is what Tesla is doing. So if you haven't seen the AI Tesla Day, I highly, highly recommend it, because for me, it's one of the best examples of data-driven robotics at play. And their vision system actually does a couple of things that are sort of important. One is it tries to get a whole 3D representation of the environment around the car. So I forget what they call it, the vector space or something like that. And that's really useful because, so that involves first you have to calibrate all the cameras, because unlike vision from YouTube and so on, if you have an embodied agent, calibration is actually really important. And it's going to be useful for doing proper sensor fusion as well, and then being able to have a three-dimensional representation of where you are, what are the other agents with respect to you. So it gives you way greater awareness. I think often I see, and I'm guilty of that, using very simple vision architectures for neural networks, but scene understanding is, computer vision is not a solved problem. It remains one of the big problems, and I think it's when you confront robotics, you actually confront some of the most interesting computer vision problems. Another thing that we have found very useful in our research is this idea of doing offline, even if you're doing just imitation or distillation during training. So you're just doing behavior cloning. It's still very useful to learn a value function using techniques of RL for that data, and then using that value function when you deploy. So it's become kind of, as shown in that picture there on the top, there's two ways in which you could learn a policy pi and a value function q. So you could take your data, just do behavior cloning in the whole data if you believe that most of the data is good, or you've thresholded or something, or you do maybe CRR. You get a policy, actually don't do CRR. CRR is the right-hand side. You do maybe distillation and so on, you get a policy pi. And then for the policy pi, just through Bellman backups or fitting the returns, there's different ways of doing that, you can quickly estimate a Q function. And usually you use the same neural network architecture in order to keep your computation down, and use one head for pi, one head for Q. And if you do that, that's very easy to do. That's a standard supervised learning pipeline with a bit of RL, but it's really easy to do. It's one of the simplest things you could do. And then at test time, what you do is you act according to pi, to the policy, but you improve that with Q. So one of the simplest ways to do this is with this thing called critic weighted policy, which is you sample a bunch of actions from the policy, you weight them according to the value, and then you pick the most valuable actions. So you basically, when you're acting, you're sort of imagining one step ahead and then acting according to that. And if you decide to imagine a few steps ahead and do more of a search, then you end up with MCTS, and that's essentially what mu0 would do. This is by far what we have found to be one of the most efficient ways of learning in offline RL. Critic regularized regression, it works, and like many 50 other algorithms now in offline RL, but it's the danger, especially when you don't have expert data, where all your data is messy, it's where it's useful. But the danger is you're iterating between learning pi's and q's during training. So I mentioned that if you had the right q's, then learning pi was great, because it was like having a teacher that selects the data. The problem is you don't have q during training, and so you're learning. And that, we are still in the field learning how to stabilize that learning. And that's not just a question of CRR, that's a question of all the RL algorithms that iterate between learning value functions and policies. So I highly recommend this as your sort of entry point into offline RL if you're not doing it yet. It's just learn a value function, learn the policy using expert data, and then try to use one of these policy improvement operators when you deploy. Another learning is this, and it's this acceptance more than anything, that as much as I would like to be designing the robots that will, fly, do all sorts of things in the world, the fact is robotics is a very hard field. It requires that we solve, issues with hardware, scene perception, and these are all open problems for which we're not there yet. So to a large extent, it is an academic field. And as such, the only way we're going to have progress is if we do the same thing as to what the computer vision field did 20 years ago, and many other fields have done since then, which is to create benchmarks. And we've seen the creation of some benchmarks for offline RL just last year, like D4RL and RL Unplugged. And now we're seeing the creation, and we've seen the creation of a few robotics benchmarks and so on. But I think we need to step this up, because it's only through the clear benchmarks that we will actually be advancing our technology. There's still a lot to be done, but step one is to have a way to measure performance effectively. And so that requires clear metrics, but it also requires software. And so at DeepMind, we've kind of taken this seriously. We've created software for agents, and we've open sourced it, so things like Acme, software for doing distributed computing, software for dealing with replay architectures like Reverb, and of course simulation software like Mujoko, all of which we've open sourced. And that sort of push for having good tools like for doing distributed computing, for doing replay, for doing, agents, is really important. I think sometimes, even like the storage, our never-ending storage from the first project, it was probably, that database was the most important thing that came out of that research, because it then gets reused by many other researchers. And this is important because in robotics, we're kind of very used to this idea that we try something, we get a video out of it, we get the paper, and we're done. And what happens then is that if you search for a robot doing X in YouTube, chances are you will find it. Like I always say one of the hardest things is tying shoelaces. But if you Google for a robot tying shoelaces in YouTube, you'll find like 3 labs at least who have solved that problem. But the solutions are not robust. And maybe they show you the video for that sort of one time that it worked, when they put the shoe of a particular color at a particular angle and so on. And we want to move away from that to things that actually work. And the same with teleoperation. I was showing you there a video of teleoperation, and I remember at some point on Twitter I said we need to do more work in teleoperation, and everyone's like, oh, but teleoperation is a solved problem. Look, watch this video. Even Jeff Bezos can teleoperate 2 arms. And anyone doing robotics seriously knows that this is far from solved, because every time you want to do teleoperation in a lab, it works out to be really hard, and before you know, you're just basically using a space nav to control, because it's probably the most robust solution. So again, consistency matters, and we need to have benchmarks to be able to evaluate robotics. And in fact, there should be some sort of benchmark for teleoperation, which I don't think there is one now in the world. And finally, as we're moving to using transformers and robotics, and this has become some sort of a hot area, using autoregressive models, I think it's a great area because it promises that we move more to generalize better. By map, it probably will be able to deal better with having robots of different shapes and so on, and being able to just have one model that works across all of them. But the danger is that in these models, you condition on past actions. And when you learn from data, either via behavior cloning or offline RL, and to learn a policy that maps previous actions to future actions, you're learning a correlation model, which is what's there on the left-hand side. But when you use it, and the policy takes actions, and then in the future conditions in the actions, but it's not aware that those actions on which it's conditioning were its own actions, then it ends up doing the wrong thing. And so this is the difference between knowing that your action was something you did yourself, like you indicated by this operator, you did your previous actions, versus there were random variables that you observed. So I guess what I'm trying to say is what I have in this quote here at the bottom. You can, a thermometer indicates a temperature with some bar, and usually that's correlated with the actual temperature of the environment. So if the bar is up, then temperature in the environment is up. But if you stick something hot to the thermometer to move that bar up, then you should not be predicting that the environment temperature has gone up. So the first part is an observation model. The second one involves you actually acting and you being cognizant that you've acted. And one simple way in which you can see this failing is if you have a dialogue. If you train with supervised learning a language model to do dialogue, and then it has to interact, if, like in this example where the environment says, what's on the menu? Then the robot says, cheeseburgers are on the menu. That's the action. The environment says, no, it's tacos. The robot says, tacos are on the menu. And then the environment gives you the same situation, what's on the menu, and the robot will answer exactly what it answered the first time. And I will, train a language model, use it for this, and you'll see that this is the result you'll get. Because you've just learned correlations. The language model does not know that it was itself that took the previous actions. There are ways around this. One is to do reinforcement learning, in which case you're actually intervening in the world, and so you can get causal knowledge. But of course, that's expensive, and there's issues of exploration and so on. And then another way, and this is why I took time spent on that interactive distillation slide, because counterfactual teaching is another way of, through imitation, get to causal knowledge and get around this problem. So those were my sort of 10 lessons. This is sort of the things that I've learned, and hopefully some of these will be useful to you in sort of thinking about what I think are important problems in data-driven robotics, and some of the findings of my colleagues and myself over the last few years. Now, finally, I'd like to have a slide that is a bit more philosophical and a bit more personal about why I do robotics, why I've cared. Even though I'm a machine learning person, I've been doing robotics, now attending robotics conferences for 25 years. And there's several reasons. I mean, the first one is, I think, dexterity, tying your shoelaces and so on. This is a big part about our intelligence, about what it is to be human. And if you want to understand intelligence, you can't get around having to eventually understand embodied intelligence. That, I think, is unavoidable. Also, as we've learned with Corona and so on, extreme events do happen, and it would be great to have the robots ready for the next extreme event. So I think robots ultimately will be essential to our survival, and it's important for future generations that we think about them and start doing the research now. Robotics has many good, useful uses out there. Like I was just listening to this beautiful podcast by Peter Beal using robots to deliver blood in Africa, and now sort of moving to also the US. But they also have terrible uses that we see on the internet and so on all the time. And so this question of safety and deliberance about the uses of robotics, I think, is important, and we should be paying much more attention to it. And to get at safety, I was really happy to see some inclusion efforts taking place here at this conference, because by and large, our biggest problem in the field, to make sure that we're sort of serving everyone and not just the few, is to improve on our diversity and be more inclusive. Just as we can, someone shared this picture on Twitter of, this is for the Natural Language Processing Conference, one of the sort of hot areas now of AI. And it shows 0 papers from Africa, and it shows just 1 paper by only authors for the whole of Latin America. At least there was once. When I last attended and gave a talk, I think it was the last talk I gave, there was 0 from those parts of the world. So we're still a long way, very, very far away from being a diverse and inclusive community. And so I ask you to go back to universities or labs, industrial labs and so on, and ask the people working with you, can we do better in this regard? Can we set some quote that is measurable in terms of hiring more people? Can we set up scholarships to help people? Can we engage and just engage in the dialogue and learn about what could we do to help with this? So I think we should all take some responsibility in doing something about this. I think I'm out of time. Thank you very much for listening.
Thanks so much, Nando. Yeah, really great to see the breadth of robot learning research at DeepMind. I agree with your warning about one-shot wonder videos. I think that's something we should all look out for. Let's take some questions then. We've probably got time for 1 or 2 questions from people here. So if you have a question, please raise your hand. There's some volunteers with microphones. I spot a hand over there. Yes, let's go for that.
Hi. Is this working? Yeah, great. Well, thanks very much for the talk. So I agree completely that robotics is hard and interesting. We'll be doing it for a long time. I guess I'd like to challenge a bit your main proposal that data is precious, and that we should be storing everything. I guess my feeling might be that, especially we're in such early days of robotics, we're working on certain toy problems or with strong assumptions or with simulators. I think a lot of that data is fairly meaningless, actually, and wouldn't it I guess an alternative approach is to, certainly run things on that kind of data, see what you learn from it, and with human judgment, turn that into theory, maybe build that theory into the next, stage of the way you go about doing things. But don't you lock yourself into a bit of a dangerous paradigm if you've just got this huge trail of data running along behind you? Doesn't that hamper you eventually?
So the cost of storing data are very low these days. So I think there's little reason not to do it. And it is true that a lot of it will be useless. Just like most computer vision benchmarks turned out to be useless. But if a few work, it's going to be amazing. If we get the ImageNet once, then I think that's going to lead to significant progress. And I guess I've taken a very strong stance here pro-data, because it's really alarming that most companies that do teleoperation never think about the fact that the users will want to store the data. So if you want to go and buy a teleoperation system, you have to do a lot of extra work to be able to sort of capture the data. And some of that data is really useful. We can actually learn better robots. And I also think we just have never done it. We've never bothered to sort of store all the data and share it. And I think if we do, and if it's only a few of those data sets turn out to be useful, we're going to be much further ahead than we are now. I think now we are in the situation where just there's no data. And so I would prefer that we start thinking of storing data, and then maybe, the answer will be between, I guess, your view and my view, which will be some good data sets will appear that will become standard with benchmarks and so on.
Thanks.
We're going to have to move to a question from FeedLoop. So my co-chair, George, is going to ask a question from the virtual world.
Yes, great. So we have two questions, but I'll start with one slightly different. So it's about the robot sketching. So the question is, how much does the quality of the sketching from like a good or very good or better expert is sort of changing the results?
Oh, how robust is it to different people sketched. So I don't think we measured that, but I do remember this was something we were discussing, because we did have a bunch of people in the project going and doing different sketches. And for that setup, sketches were the right way to get at it, because someone, it was for stacking, it's very clear that there's sort of an end goal that is better than before. But I also should warn that sketches will not always be the solution. There are some tasks for which the way to provide feedback is not via sketches. And it's a question of thinking about the problem, what's the best way to provide feedback.
Wonderful, thanks. So this was by Brian Chen, and now another question by André Mouton. He asked about, he agrees that benchmarks are great, but there's a risk that these benchmarks are not super representative of the real world, right? So we see this even in computer vision, where we have a lot of benchmarks. Often these state-of-the-art methods, they only report summary statistics, then they look great, but they don't really work in the open world, in the open set problems. So what's your take on this in the robotics domain?
Yeah, so that's very true. I think especially when a benchmark gets maxed out and people still keep publishing papers on it, and like, as it's happening in computer vision, that's not great. We're still publishing papers on MNIST, but at the same time, the benchmarks are useful to improve our technology, because even something as simple as MNIST has been so useful for the design of algorithms, through decades. And I think in robotics, we are so far from having good offline RL agents. We are so far from knowing how to, do scene understanding and reason, that I think it's really important that we come up with benchmarks. We will max them out, and then we should create newer benchmarks that are harder. And I think it is a question of making progress on sort of iterating between creating benchmarks, being able to attain what those benchmarks do, and of course always be engaged with industries as well, so to make sure that these benchmarks will at the end of the day be solving problems that actually are useful in terms of manipulation and locomotion and so on.
Do we have time for one more question? Or okay, so thanks everybody, online and here. And so, is there some other announcement then?
I'm just going to make a quick announcement about
Please.
lunch, but we can thank Nando so much.
Thank you very much. Thank you.